Thank you, Jessica. By the way, I saw the videotape last year, your presentation. I loved it. It's wonderful. I hope I can talk to you about current U.S.-China trade war. But Larry must be doing something, make a statement. This year, I think he invited at least 3 or 4 people with a biological clock that is made in China. May have some tax benefit of this. My talk is about how to learn from our immune system. I'm from Hassan-Narfa Institute, which is a nonprofit biotech institute in Huntsville, Alabama. And we focus on genome and genome research. Rick Meyer, our director, was at Stanford and part of the Human Genome Project. And the institute also doing main 3 things, basic research and economic development, spin-off companies, and education. And as a part of that spin-off companies, I started 5 companies and sold 2 already. And so it's an entrepreneur part of the institute. So when I joined Hassan-Narfa in 2007, I was giving a few $1 million startup fund. And I think I was really lucky at that time to have this money, don't have to worry about writing papers and getting grants, and really think about what should I do in the next 5, 10 years. And before I did anything, I spent on, because all my life I've been doing diagnostics. So I keep thinking about how can we do things differently. And diagnostics is simple enough. You get disease signal from patient sample. But the sample could be direct, invasive, or non-invasive. You get a signal that is quantitative or qualitative, yes and no, or high or low. But it's always come with a noise. And we want to get a diagnosis that's directly related to the disease, the causal effect. That is, for example, you get a bacterial infection, you detect the DNA from bacteria, that's true. But more than often, we get an indirect diagnosis, like diabetes, you're measuring sugar. And so the best diagnosis everybody really hoping for is to get a non-invasive sample, get a qualitative signal, no noise at all, and directly diagnosing the disease. So that's the dream that the diagnostician will really want. But look at how we're developing diagnostics. We've been doing the same thing for all these years. First, we get a group of patients, have the same symptoms. Then we do many years of basic research, find out what is the cause of the disease, what is different from other disease, what is different from normal, and then we claim we find a disease signal. Now we develop a methodology, a technology, a machine to measure that signal from patient sample, and then we commercialize it. So we spend most of our time and money to identify the signal. And by the way, that is science. From there on, it's technology. Science should be spending money from the government, and then you commercialize, and that's where the company is taking over. But the problem is, identify the signal require human knowledge, and detect that signal require human technology. And human beings, I believe, are always limited. So how can we bypass these limitations and try to find a way to get the diagnostic signal faster and quicker and easier? I think it's this Chinese feature, as we always try to find a shortcut. And the shortcut here is to learn from nature. And the best diagnostician in nature is our immune system. For each one of the potential diseases, there's a antigen exposed, something wrong with the cause, the enemy. And our immune system, either Tcell or B-cell, have this receptor on the surface recognize that. So each one of the T cell, B cell actually become a disease sensor that can detect the disease signal, very specific, very sensitive, and the signal is in our blood. So that is the shortcut. And so I went out to raise money. This is the picture I used to talk to the investors. I said, our immune system have to deal with the internal threat and external threat. Too aggressive, deal with the internal threat, external threat, we got inflammation. Too weak, we get infected. Internally, too aggressive, we got autoimmune disease, and too weak, we get a cancer. Both of these aggressiveness lead to tissue damage, and both of these weakness lead to something abnormal growth, either bacteria growing or the tumor grows. That's about all the human diseases. Either something broke or something growing. Doesn't matter what happened, there's suppose a group of disease-specific antigen expressed at the wrong time and the wrong place and the wrong volume, and our immune system already recognized it, detected, and trying doing something about it. So if we can read the diagnosis made by our immune system, we'll become better doctors. So I raised $15 million and tried to do the work. We started in 2007 actually. But here is a challenge. Each one of T cell, B cell receptors is supposed to be a protein. And we all know one protein is supposed to come from one gene. But in our immune system, and only in our immune system, they have these special mechanisms where a group of tiny little genes, variable genes, they call the variable genes, nested to each other in our genome, and then a group of diversity genes, juncture genes, and C gene next to each other. But in the immune system, in the thymus or bone marrow, there's a special enzymes can shuffle these, recombine these, will randomly taking only one of the V, one of the D, and one of the J to put them together. And between V and D and between D and J, without any templates, the enzyme will randomly inserting 20, 30 base pairs. Each base pair you have A, C, G, T, 4 possibilities. So that's how our immune system making up to 10 to the 15 or 10 to the 25, that many different T cell, B cell receptors. And every day our immune system just making these new soldiers, and that's what we are sequencing, using next generation sequencing to sequence the VDJ rearrangement. More specifically, it's a CDR3 region, or complement determined region 3. That is where the disease sensor is, because that's the area of stretch of DNA or protein that bind to antigen. That's all the science there is for the talk. The methodology is quite simple. You get a patient tissue or blood, you get the DNA, RNA out, the genetic material. This is the yellow part, the multiplex PCR is the core technology that we developed. Basically, you use a pair of primers, a synthetic DNA, franking a piece of DNA, and then you throw in enzyme, they will amplify this piece of DNA. But my contribution to this is multiplex PCR. In one system, you throw in hundreds of thousands of primers, they will amplify hundreds of thousands of targets, and that's why the immune repertoire can be amplified from a sample. And then you use the next generation sequencing to study them. So we published our paper, first paper in 2009. We filed a patent in 2008. We were the first one to file patent, award patent in this field. In that publication, for example, one study of, I do a lot of my blood, so this is my blood. And we got one blood draw, we get 280,000 effective reads, means you find the VDJ rearrangement, 250,000 unique CDR3 sequences from one sample. And when we published this paper in 2009, Gene Bank the past 20 years, all the scientists in the world only studied and deposited 1,200 sequences. We're dumping almost 1.5 million with one study. So it's a huge amount of information. And each one of the study, there's huge amount of data, but you will get what important is a list of CDR3, the clone types. Each cell have one unique CDR3 like their barcode, and their frequency in the sample. And we have a 2D map, 3D map, and all the other things. But I want to draw your attention to this beautiful clone type frequency map. Each one of the little square is a unique T-cell receptor, unique T-cell clone that potentially recognize an antigen or enemy. Imagine there are different soldiers with different equipment that can fight different enemy. And when the T-cell get engaged in an antigen, they will get expanded, and if they are being effective, they get more clones, they get more resources. And that the size of this square is the frequency of that particular clone in your sample, in your repertoire. And by the way, this is so beautiful, it shows up in many journals cover. So how are we going to use these? It's just like economists describe economy with a GDP, unemployment, durable goods, sales, and all these indexes. So we created a whole list of indexes to describe the immune repertoire statically and dynamically. And the first three, the chronotype index and diversity index and essential index, I'm using it to evaluate health. We'll tell you how we do that. The sharing index can be used to identify specific diseases. And the other index is used to monitor treatment. Chronotype index is really measures the number of chronotype in a sample. For example, the top and down are two individual. The top one, we studied almost 300,000 molecules called reads. That is when you sequence the DNA. After sequencing almost 300,000, we only find 6,500 unique clones in this individual. The bottom individual, on the other hand, almost sequence about the same, so 280,000, but find 20,000 unique clones. So per unique reads, how many unique CDR3 you found is the clonal type index. It's like asking the question, if a country have enough soldiers, how many soldiers you have? The diversity index, on the left is a healthy individual have a lot of different clones and ready for all kind of fight. On the right is a leukemia patient. One clone take more than 95% of the resources. So the diversity index is asking how many top clone contribute to 50% of your diversity. So the diversity index here say D50 equal to 33, means when you have 50% of your total resources is counted for by 30% of the top ranked clone types. And the lower one, if every clone have equal resources, then they're on the line, on this dotted line. But the lower one, you can see they have less diversity. But what this means is 50% of the resources occupied by only 7% of the top clone. So that is a diversity index. And you can see this is a mouse study, not human. With aging, you lost your diversity. And because everybody have basically the same body build, about the 10-liter blood, so our capacity is capped. When we were born, our immune repertoire have the maximum potential to deal with all kinds of infections and the diseases. But when we're close to the end, we were growing older, our immune system actually have the maximum efficacy, but you are losing your potential and the capacity. So that somewhere in between is the trade-off, and somewhere in between is health. And essential index is also interesting. We developed a Google-like search engine. You put in a CDR3, it will tell you how many people in our database have that particular CDR3. So far, we already sequenced more than 80,000 samples. We find more than 4 billion unique CDR3 in our database. So we can tell when we pull 1,000 sample individual together, you find 3 billion molecules studied, 75 million unique CDR3 sequence. 81% are private, not shared. Only one person has it. 12% barely shared, 7% shared by less than 10% of the population. But there's a small percentage shared by almost everybody. So we don't know what this very public CDR3 bind to, what their antigen they interact with. But the fact that everybody has it must be because they are very important. This probably not causal. So we have this long-tailed distribution, and you can see the cord blood, all these gray ones are public CDR3. So when we're born, we have a very high concentration of public CDR3. We're getting older, you fight a lot of private wars. And so it tends to be the public CDR3 may be recognized internal antigens that during development that you exposed. So the essential index basically measure taking 100,000 of unique reads, how many of these top 1,000 everybody must have CDR3 in your sample. A young person, 24 years old, 100,000, you can find 600 of these very public CDR3. An older gentleman only find 60. So here is a question then. How do we measure health? I think healthcare really need a objective measurement. We say we are sick care rather than health care because we have no measurement of health, objective measurement of health. It is difficult. It's asking, are you healthy? It's like asking, are you happy? And because we are using diagnosing of disease to measure health. We say you are healthy if you are not sick. Based on that logic, you have to run all the tests in the lab and you're all negative before we can say you are healthy. So that is, again, I think this is a Russian day. We're talking about Anna Karenina principle where all happy families are alike and each unhappy family are unhappy in its own way. But I want to say all healthy individuals, all healthy people are alike and all sick patients have their own sickness. Then what is common in healthy people? They have a good, adequate immune system can prepare them and fighting for different disease. So how do you know you are ready? Your immune system is ready and prepared. We can ask 3 simple questions. Do you have hired enough total soldiers? Is there enough active duty soldiers? Or do you have enough reserves? And these are answered actually by the 3 indexes that we created. Chronotype index shows you, do you have enough total soldier? And then active duty is the diversity index because we rank the top dominant clones and counting those. Those are active ones, or they are fighting or just fought a war. So imagine you have this status. You are at peace but vulnerable. That is like a newborn baby. You are at peace but ready to fight. That is healthy adults. You are at war but winning. That's acute infection or acute diseases. You are at war but losing. That is chronic diseases. You are at peace but you already lost. And that is the end of the disease stage. And for each one of these, you have a different allocations of total soldier and active duty and reserves. And that is measured, correlated with these 3 indexes. So that is how we can use these to evaluate health. I give you some examples. On top row are healthy young adults, their repertoire. You can see how beautiful they are, how diversified they are, and some of them bubble up, interacting and treating some disease. And the second line are really active, some acute infections and disease they are managing. And the lower line are their chronic disease. The top line here are renal cancer patients, and the bottom line 3 are leukemia patients. But need to warn you, though, patients may also have a very nice wellness score, and obviously, it's a test always have a false positive and false negatives. So that is evaluating health. How about diagnosing disease? We developed the sharing index. Each one of the row is unique CDR3. Each one of the column is a patient sample. The left half is a patient with a breast cancer, and the right half is normal controls. So some T-cell receptor only show up in certain patients, not in control. So the way we study it is you study patient and a control, you find the unique CDR3, you ask which one only show up in patients, not in control, you use those as a signal. And then you take a test sample, only take the dominant one because we want to ask what your immune system is working on today, and then check with the disease signal, have any overlap or sharing. So in this picture show, each one of the red dot is a patient sample. Y-axis is how many disease signals show up in this patient sample. This is a tuberculosis patient and a control. This is a training data sets, identify a signal, give me another group of patients, we can detect more than 90% of the patients. And the latent TB, half of them have signal, other patients don't. And the same thing for type 1 diabetes. CMV is a viral infection. IBD is autoimmune disease. And liver cancer, breast cancer with collaboration with Hong Kong and Taiwan, and renal cancer with Johns Hopkins, and heart disease and so on. This is what we started about 7 years ago called R10K project or Repertoire 10,000. Hassan Narfa, as a nonprofit research institute, organized this project. Anybody can go to these websites and download a guideline and write as a proposal by answer 5 simple questions. The disease is important, currently do not have very good diagnosis, obviously linked with immune system. Once biomarker is found, you know how to use it, early diagnosis or treatment guidance. You have a sample in the freezer and ready to go. Satisfy that, Hassan Narfa give you free reagent, free sequencing, free analysis. You get to be the first author to publish, and data will be publicly shared once the project's done. So we have 30-some disease under study and still open for enrollment. And we can also use the same technology for treatment guidance, especially for the current immune therapy. This is a study done with liver cancer patients treated with anti-PD-1. We measure their immune repertoire before, during, after treatment. And what this shows is if your dominant clone, individual's dominant clone, more than 20% of the dominant clone after treatment become upregulated, you had a better chance to respond to the patient, to the treatment. What this means is I think our immune system is really smart. If they feel they cannot fight a war, they will negotiate a truce. And the anti-PD-1 treatment basically go there to tear up the treaty and say, let's fight again. But the reason there is a truce, treaty signed, is because the immune system don't have the confidence they can win the war. And therefore, if you tear up that treaty, you may only have a 20% chance to win. So what we are trying to do is, can we figure out who belong to that lucky 20%? This is another test show we have a new assay that can evaluate all 7 chance of T-cell, B-cell receptor from one sample in one study. And this is show renal cancer patients before treatment, we can already identify those have a better diversity will respond to the treatment better. it's a resources. If you have resources to fight, you have a better chance to win. And so we're getting ready for action. The company have all kind of product and service. And for example, we have automation. You can put a sample into the cassette, put the machine, the library is made automatically. And we try to get a FDA approval for this new white count. White count being used for 100 years. Now, at molecular level, we can tell you your immune system, T-cell, B-cell receptor, alpha, beta, gamma, delta chains, and heavy and light chain, all the 7 genes can be studied from one sample in one reaction, in one cassette, and giving you new biomarkers, the 33 values, T-cell, B-cell value, alpha, beta, gamma, delta value, and alpha to beta value, all kind of indexes and ratios help you to find association, not necessarily causal. For example, this is a patient before and after treatment, cancer patients before and after treatment. You can see after treatment, the B cell, there's no correlation with the before, but the T cell correlation is still there. So with this 7-chain analysis, you can see the overall change. What else? Now, we also developed a direct-to-consumer test that allow you to evaluate health. We call it My Immune Bank, not My Man in Black. But we published a paper for, you can just take a fingertip blood, spot it on the filter paper, dry it, put the envelope, send it back, and we can measure the immune repertoire and put it on and show it to you. So the correlation between on top is a filter paper, at the bottom is a regular blood, and they correlate well. And so we come up with a sample collecting device, and we come up with an app, so you can buy the device, take your sample, and you can measure the immune repertoire, the wellness index, anytime that you want. By the way, I have some samples, anybody interested, free for you. How do you use this? This is one of my friends, I see Art is here, Michael did a marathon. And this is a before and after his marathon run. This is a before in the morning and after and the day after. And you can see after the marathon run, the T cell went to the tissue and repair something, and second day it will coming back again. A younger person did the same thing, but he didn't run marathon that often, and you can see his T cell go back in a hurry, and then coming back. And this is interesting, this is a repeat. Before and after cryopreserved self-lymphocytes. There are many companies in China do this. It will freeze your lymphocytes today for your future use. And this is an experiment before and after the infusion of herself after being stored for several years. This is me again. I was adventurous without my wife knowing. I went to China, got an injection of stem cell. And this is before, this is 1 day after, this is 3 days after, this is 1 week after, and 2 weeks after. So at day 3 and 1 week, you see your diversity increased, but it go back to normal after 2 weeks. And we can also measure traditional Chinese medicine now. So we have a doctor. This is one person before and after traditional Chinese medicine. Traditional Chinese medicine is hard for Westerners to understand because the diagnosis is strange and the medicine is strange. But all these herbs, you just have to imagine, all these herbs are growing in certain environment in the soil, and they have combating all these bacteria in their environment. So in a way, they are antibiotics, a mixture of antibiotics eating into your guts to deal with your microbiome. And if your microbiome don't fight, which take about 1/3 of your immune resources, if there's no fighting here, you may actually release some energy or potential to treat your diseases. And so I think this is one way to show the efficacy of traditional Chinese medicine. By the way, it's also personalized arts, and you can hang it on the wall before and after your immune repertoire. So we can also learn from immune system. We developed technology to study single cell. We developed the software analysis, not only pairing the alpha, beta, or heavy light chain from the single cell, but also giving phenotype information, cytokine, transcription factor, and surface marker from the same single cell. And this is important because now we can not just learn the diagnostic capability of our immune system, but also treatment capability. And for example, in B cell, we work with several researchers at NIH. They're developing vaccines. So I actually had a patent a couple of years ago applied. Inject myself 2 years in a row the flu vaccine. And before my second vaccine shot, I got my blood. And day 3, day 7, day 21 after the vaccine shot, I got my blood. And I see the upregulated clones after the vaccine stimulation. And I clone the heavy and the light chain and pair them together. And so they can demonstrate them, they can bind to the antigen. So I can get a monoclonal antibody against the antigen without go through hybridoma just by sequencing the patient blood. Imagine if there's an outbreak of Ebola and you find a survivor, you sequence the blood and find the cure. Basically, the monoclonal antibody can neutralize the bacteria. So you don't have to wait for many years to develop a vaccine. Now you have a treatment. So this is what the NIH people did for a dengue vaccine, and they actually find a monoclonal antibody can bind to the dengue antigen. And we have a Chinese doctor that come to our meeting a couple of years ago, learned about this technology, but he has a little twist. He injected a monkey with a flu vaccine, and using human primer amplified from monkeys so they can get the monoclonal antibody from monkeys. So that's what you can learn from B cell. You can also learn from T cell, which is cell-to-cell combating. And that's what we plan to do with a group of scientists financed, supported by Jiangsu province. And we're going to start an applied precision immunology institute to do the RNK Chinese version and also cell therapy, and as well as developing a new machine. Okay, what else we can learn? Here is an interesting picture. I think many of you actually saw the similarity of this picture with the famous Gini index. The inequality, the accumulation of wealth and how many people, and the absolute equality and inequality, right? How about these? Can we learn from our immune system and have a better tax structure that is actually healthy? But I think what we learned, I think, at least from this point, is there's no tax structure is good for everybody. When we were born, we worried more about infection. When we're close to die, we worry about more of internal mutations. And a country is the same. At different stage of development, you need different strategies. And that's what I think we learned from our immune system. So to summarize, I think health is all about balancing the resources and prioritize what you're going to do today and tomorrow. And wellness can be evaluated without deal with disease. We've been focusing on the disease too much, and we need an objective measure to evaluate health so that you get motivated to become healthy. I get up in the morning to run, I know how much I run. But you do anything good to yourself, your immune system, you don't know. And that is why we need a test. The repertoire sequencing diagnosing disease also have a potential to become really the ultimate diagnosis. Basically run one test from one sample to match which one of the signature you are using or which one of the disease your immune system is working on today. And the social impact is huge because imagine you have a test testing hundreds of diseases and the payer only pay for the positive result. Now you are paying everything. And so that is require totally different thinking about how to implement these. Another thing we learned from our immune system, I think cancer is really a sign of battle fatigue. And if that's the case, do we really need to fight the war? Or can we negotiate a truce? Maybe for majority, many of the patients, to amend the peace is a better strategy than waging a war. And also, I think the best doctor can also tell us something about improving society. I think that is my shot for a Nobel Prize of economy. Thank you very much.
Okay, sorry. So what we know already is that Alfonso was dead wrong, and that the beauty is in the mind-boggling complexity of what God or nature created, if you have someone smart enough to find it. So let's take some questions. Oh, you have. Oh, yes, I'm sorry. Wait for the microphone because this is all being videoed and connected to...
You have it right here?
Okay, go ahead.
That was really elegant and beautifully presented. So you have this fantastic diversity of these receptors, but that diversity is way, way greater than the diversity of the antigens, right? So I wonder if you can take advantage of that diversity to reduce the understanding of what the key antigens are that predict progression or recovery or all the outcomes that you want to predict, because the complexity is so great. So I wonder if you could take advantage of that and do massive parallel pull-down experiments, because you have also the best negative controls. You have huge diversity of the irrelevant ones, which is what makes the pull-downs more, will give you meaning on the pull-downs. So can you do that and have an understanding of what the relevant predictive antigens are?
Yes, I think we need to do a whole lot more of the sequencing and the data analysis. The data analysis really is the key, and using different artificial intelligence, different methodology, different algorithms to figure out. There are also a Japanese scientist that based on known crystal structures calculation to predict what the antigen may be. So the sooner we get to that end, the more we learn more. However, I think before even we get to know the antigen antibody binding specificity, we still can learn quite a bit from our immune system.
Good. So you went through the diagnostic part faster than I could assimilate it. So I have a question for you.
Yes.
About, in terms of the diagnostic capacity of this beautiful work, could you tell us something about the sensitivity and specificity of, say, stage 1 breast cancer versus stage 1 renal cancer? Something that is a real diagnostic problem. And I couldn't tell the staging of the cancer versus normals in what you showed.
Yeah, that's a good question. When we do the R10K project, a typical R10K, we study 100 patients, 100 control. You'll find about 7 million unique Tcell receptors from the patient's group. And after you analyze them, you find 300,000 are shared among patients. But when you look at a control, majority of these 300,000 will be also in patients. And you only end up with about 3,000 that exclusively in this patient's group, not in control. However, the good news is these 3,000 are qualitative markers because they don't show up in control. So any one of them show up, its sensitivity is already good enough. So to answer the question about sensitivity and specificity, because when we do study, we study one disease, we use every other sample as a non-disease control, even though they have other diseases. And so these 3,000 is really unique and specific. Each patient may only end up with 100 of these unique CDR3s. And then that's how we use into diagnosing disease. In terms of staging, I think that is challenging because a lot of this staging is man-made classification. What we try to do is to view the problem with immune system's eye, what they are dealing with. And therefore, sometime in the early stage of the disease, you actually see stronger signal because your immune system still put up a fight. And so that is how you correlated that. I think the most important question we want to ask is the outcome. Which information is impact the outcome?
Thank you, Doctor. I'll try to keep it short. My question is regarding the traditional Chinese medicine. I found that really interesting because I guess a lot of people in the West kind of think that's maybe like pseudoscience or something like that. But in Boulder, we have a lot of naturopaths. When I went through my Hep C treatment, it kind of made me sicker than I was the first time. It was more like a clinical trial. But I did traditional Chinese medicine, and that put my hepatitis C into remission for many years until I was able to go back into the better protocol. And of course, now it's easy peasy, I guess, to get over your Hep C. But if you could just comment really briefly on traditional Chinese medicine and maybe virology or something like that. Thank you much.
Thank you for interested in that. Traditional Chinese medicine being practiced for thousands of years. So it's been in clinical trial for all these years. The problem is there's no control. Therefore, Western physicians, scientists don't agree and don't recognize it. So, and also there's no, it's all experience. It's practiced based on experience. And there's no documentation, there's no records. So we want to provide something that is measurable and before and after. So we actually engage in a study in Hong Kong where you have a diabetes patients and they've been classified based on Chinese medicine into 4 or 5 different classifications, and each classification you divide them in control group and treatment group. The control group only using Western medicine, and the treatment group using both. And then if you have a samples, you measure these. All these results will be recognized and acknowledged.
We have time for one more behind you. Oh, I'm sorry.
Hi, this is an amazing talk. Have you looked into patients going through anaphylactic shock?
No.
Well, I have a very severe allergy to tree nuts, so I volunteer to, if I I would be very, I mean it is a severe immune reaction, and so I'd be very curious to, and it lasts several days, and it's treated at the hospital, and I mean it's a life-threatening condition at that moment, so it would be really interesting to see what's actually going on, or see if it's.
We have time for one more. Lady right back there. Thank you.
Thank you very much for your talk. I'm really fascinated by the elegance of your thinking, and particularly about the concept that health is all about the balancing and allocation of resources. And my question is perhaps a little bit more philosophical, but since you went there with the economy, you know, healthcare is one of our greatest costs in our society. And the greatest preponderance of our expenditures are at the end of life. And so I'm just really curious about your thinking about how we allocate our resources and how we might, as a society, do better in terms of honoring our aged and those who are dying and at that stage of life.
I actually want to do a study at the end of age population, end of stage, you know, patients in hospice care and to see what their immune repertoire looks like. But when I go out to talk to people, insurance company, what kind of insurance people are interested in this? Life insurance people. They want to know when a policyholder will die. And so we don't know if that is doable, but I think in a way, measure the immune repertoire, at least know roughly how many fights you can still put up with. Thank you.
Jian, thank you for a fabulous talk. And